Okay, everyone. We would like to get started with the second day of the ARD workshop. Hope you have enjoyed the first day and the dinner last night. This morning we have 4 presentations in the morning session on fusions and standards. The first one is by Rens Masselink from Satelligence.
Thank you, Hamid. Well, good morning, everyone. Thanks for everyone coming here so early. Nice at 9 o'clock in the morning. And thanks to Planet, Radiant Earth, USGS, and all the other sponsors for making it able for us to be here today. So my name is Rens. I'm here together with my colleague Vincent, and we are here representing Satelligence. I will first tell a bit about Satelligence, what we do, and then how that relates to the topic of ARD. Satelligence is a social enterprise. We're based in the Netherlands, was founded in 2016. And our mission is Earth observation for natural capital. So we use Earth observation for good, basically. We work mainly in the tropical belt, in countries like Malaysia, Indonesia, Ghana, Ivory Coast, Colombia, and Bolivia, and we work in the soft commodities sector. At Satelligence, we think it's very important that we all go into the field. Everyone gets a feel of what they're actually seeing on the screen, so not just solving the problems behind our desk and looking at remote sensing images, but actually knowing what's in those images and actually seeing them. So even our software engineers, they all go into the field, talk to clients, and go visit, for instance, tropical forests, oil palm plantations, whatever. So some of our clients, we work together with NGOs like WWF, Rainforest Alliance, with financial institutions like the World Bank, development banks, and ING, but also with food production companies like Mars and Unilever, or commodity traders like Bunge and Cargill. We work together with some universities in the Netherlands, TU Delft, University of Wageningen, but also, for instance, with the World Resources Institute. So our main product or service is what we call Smart Forest and Commodity Analytics, which what we use to help NGOs and, for instance, companies in the soft commodities to answer these kind of questions. So how much deforestation is happening or has happened in my either investment areas or, for instance, if we're talking about NGOs in protected areas. We have a platform for that where users can log in, a sustainability manager can log in, and very quickly see where his attention should be focused, so where he should look at. So he can, in a very clear overview, he sees what's going on. And if you look here and you look in the next screen where there's more detail, you see that there's no satellite images there. Our clients don't really care much. They just want to know what they have to do. And then if you go one level deeper, then you can actually see of a deforestation alert what is the underlying satellite imagery. So I have some examples of how we do this. So currently we use sensor fusion of 3 platforms, Sentinel-1, Sentinel-2, and Landsat. Using the 3 platforms, then in most places in the Earth we can get almost daily observations. We use a probabilistic method to combine the 3 platforms to, we say per platform, whether what the probability is of deforestation. We combine the 3, and then we get a probability of deforestation. This is an area in Bolivia where we work, and just as a quick example to show what this looks like. So this is a Sentinel-2 image, January this year, and then running our algorithm for a whole year, for 2018, we can say up to the day at what time these areas were deforested. So this is a combination of all the sensors. Light colors mean early in the year, and dark colors mean later in the year. So this is basically what we use to feed our system. Another example of just using Sentinel-1 is in Ghana, where there's a lot of illegal gold mining going on. These are all in the riverbeds, so that's why you see this dendritic pattern. And you see all this deforestation happening in just 2 years. So to do all of these analyses, we basically create our own analysis-ready data in-house. So we make the analysis-ready data and we use it ourselves. So all of this we do, we have all these pre-processing steps. We have them in separate Docker containers. We run them on Google Kubernetes engine, so it's highly scalable. Basically, we can do the whole world in a day if we need to, or less. But the thing is that this whole step of pre-processing, like for instance Maria of the Climate Corporation said yesterday, we're not so much interested in that. We just do it because we cannot get those data with that quality from anywhere else. So we do it ourselves. But preferably, we would just focus on the analysis part and leave all of this part to someone else. And we could just get it from somewhere and focus on what we're good at, which is the analysis part. This would save a lot of resources and a lot of money for us. So for the remainder of this talk, I'll basically go from the assumption that we are a user of analysis-ready data, which we will get from a data provider. And then this title, which is just a catchy title just to get you all here early in the morning. But then here, it actually has a lot to do with pre-processing. But so here are 4 statements that are important for us if we were to be an ARD user using data from someone else. So I'll go to these, through these in a bit more detail, but so not all ARD are created equally. One ground truth becomes many ARD truths. Artifacts devalue the term ARD, and if we do nothing about provenance and versioning of ARD, users are going to be in trouble. So first off, so up to now, there's not really a fixed single definition of ARD, but the question is, do we want that? Because if we do that, it limits user flexibility. But if we make it, leave it completely customizable to the user, then what does the term ARD even mean? So there's a question we have. And if ARD should be user-defined and customizable, which we think it should be, because if we were a user of ARD, we would want it that way, then why are, up to now, most data providers only offering one fixed type of ARD, like a cloudless mosaic, or just one fixed type of cloud masking, for instance? We want, for different applications, we want different types of ARD. And us as users, we would ideally just have an API where we could have, say, an area of interest, say which kind of algorithms we want to have applied. Maybe in the case of SAR, we want to choose a type of speckle filter. Maybe we want a very aggressive cloud masking, or maybe not. All of these things we would like to be able to change. So for the second and third point, the artifacts in analysis-ready data, and that you get different ARD truths from one ground truth. I have an example using Sentinel-2. This is an area in the Netherlands. I chose a potato field on the bottom of the sea. And you say, but this is not on the bottom of the sea, because it's clearly agricultural area. But if we go back a bit in history, and if you look at the Netherlands, what it looks like now, looks like now, and you look at the area of interest there, and we go back not even 100 years, then the Netherlands looked like this. You have a big inland sea, and if we plot the outline of the Netherlands now, you see that all of this area is basically a boulder. So 100 years ago, that was all sea, and now it's agricultural land, one of the most productive in the world. So back to the field. I took 3 sort of ARD sources. Google Earth Engine, which uses send to core. I used the standard quality band to do cloud masking. Then Sentinel Hub, which also uses Send-to-Core, but I used a different cloud masking algorithm. And then we have our system, which uses Force and Fmask. If we look at a single date image, we don't really see that many differences. Sure, there are very minor differences, but at a first glance, it's almost the same. So far, no problems. But if we look at time series, and we look at the time series of the past year, then suddenly we see quite a lot of differences. If you look at the top in Earth Engine, the middle Sentinel Hub, and the bottom R system. You see, for instance, in Earth Engine, there's not the decline in the NDVI at the beginning of the time series, where the other two do have it. Also, Sentinel, especially in Sentinel Hub, you have these valleys, these outliers in the bottom, which are remainders of clouds, cloud artifacts, which are also present in the Earth Engine data, but even also in our data. Just to quickly touch upon Sentinel-1, we use it a lot. We heard yesterday already, Sentinel-1 is difficult, it's scary, we don't really know. But just as a general idea that these are kind of the things we are dealing with that are sometimes difficult to solve, especially the top one, because we have to deal with low resolution DEMs. And also the third one, there's speckle. You need to filter it, but which kind of filter do you use? And similarly for compositing. So just to show you an example, this is the island of Sumatra, and on the right you see a part of Malaysia. So this is actually a quite nice composite. Here it works pretty well. You see in light purple, you see all the palm oil plantations. So they pop out really nicely in Sentinel-1 data. But if we look at a very dry area in Niger, in Africa, for instance, there you clearly see the scene boundary still. So there it's much more difficult to solve this. This is from a year ago. We're doing much better now, but this is still something that we're solving. Lastly, but I think most importantly, is provenance and versioning. Yesterday we did hear some people, also in our breakout group, we talked a bit about provenance, that users should or need to know where the data comes from, what has happened to it in between, have an idea about accuracy, error propagation, etc. Then there were other people saying yesterday, yeah, but users are not interested in that because they just want to have good data and they don't care what has happened. Well, we disagree because we think, especially if we were users, we think it's very important to know where the data come from and what has happened to it. And then versioning, we haven't really heard anything about it yesterday, but in our view is very important because if there are changes in the preprocessing, so be it Send-to-Core, Snap, whatever other software you use, that means you change the ARD products. And if you change the ARD products, suddenly your results are not reproducible anymore. Which means that for us in a production environment, we wouldn't be able to use this because if the ARD data changes, we would need to recalibrate our models or retrain our models. So this wouldn't work for us. So a thing we could think about is versioning systems, maybe using sparse matrices for just keeping track of the changes, or even better, not store the results at all. Just do the preprocessing on the fly. Being able to just say, I want ARD version 1.2, create them for me, and deliver them. So I think for us, as for these 2 days, what I think for us would be important to talk a bit about is are these kind of questions. So should we make a strict specification for ARD or not? Should we strive for a single truth or not? Like if I ask for an NDVI at one data provider and I ask for the NDVI at another data provider, do I want them to be the same or not? And do we need minimum requirements in terms of quality before we can call something analysis-ready data? And what are good approaches for maybe not so much provenance because that's maybe not too difficult, but if we look at versioning of ARD. So with this, I'd like to leave it. Thank you all for your attention. and hopefully we can discuss some of these things these days. Thank you.
Any questions for Rens? And I appreciate if you stand by the mics if you want to ask any question. I will ask question if you don't. Okay, so you mentioned the pre-processing versus being a user of ARD. Yeah. So would you prefer if there was a system, a platform, that would give you a kind of a modular pre-processing, that you select those modules yourself and say, okay, do the processing on the fly for me, generate my ARD. Would you be willing to pay for that versus the storage of the data?
Yes, obviously, because currently our main costs are developing the pre-processing, maintaining it, and then the pre-processing itself is computing power at Google, and then the storage is also quite a bit of money. So we're now in the process of changing this pre-processing as well to looking at like what is the amount of time we can store certain pre-processed tiles, and when do we need them again? So when is it worth just throwing them out and reprocessing them whenever we need them? Because we have it running now on a Kubernetes engine, basically there's very little time it takes to process it. So yeah, so we have to calculate exactly when this switch happens. But yeah, no, we're definitely able to pay or willing to pay for it, yeah.
Any other questions? No? Okay, thank you.
No, all right.
So next we have Alireza from the Climate Corporation.
Good morning, everyone. I'm Alireza. I work at the Climate Corporation. The talk I'm going to give you today was supposed to be given by my colleague Peter McLeod, but he couldn't come to this conference, and so I'm presenting it in his place. It has been kind of a collaboration between both of us. This is something that we have been working on over the last few months. So at Climate, we use a lot of satellite imagery, primarily for generating products for our main customers, who are the farmers in the field. What we essentially do is that we take a satellite imagery like this, we crop a small portion of it, do further analysis on top of it, and generate a map. This is like an example of it. It's a vegetation health map, like an NDVI. We do have our own kind of algorithm or model that generates that, but it is very much like an NDVI image. We also use these same kind of imagery for doing other things within Climate. We use them to develop the models that later on turn to those maps. We use them for a lot of like analysis and machine learning training and other things internally. We do have a fairly large science team that use satellite imagery for a lot of those use cases. The reality, though, is that it's never as simple as this. What we are trying to deal with is usually more like this. We usually look at time series. We usually need to know the change over time, which really means that we never deal with a single satellite imagery. We usually have multiple images, mostly of the same location, and we have to turn them into maps or use them within the science. But again, it's not even as simple as that. We don't even deal with one single group of imagery. We bring them from multiple sources. Sometimes we combine them, sometimes we use them differently. Sometimes they're like other versions of the same satellite image. Sometimes it's the cloud mask that we have generated that has to be used along with the original image. Sometimes it's ARD. But again, it's not as simple as that. We actually, our typical process looks more like this, where we have all of these images in the cloud. We have to kind of narrow them down. And then we have to even narrow them down further by some extra information, for example, like the cloud. In a lot of our cases, our fields are very small, and even if the big parts of the image are covered by the cloud, there's still a chance that the part that we need is not covered by the cloud. So we actually have to get all of these images, open them up, look which parts have cloud, which parts doesn't have, and reduce it to a small number of images, and then create those things. But again, it's actually more complicated than that. We get those images in one form. We try to improve them, make them ARD, or something like that. Then again, reduce them further to a smaller batch, and then create those maps from them. And so this is the problem that I think a lot of people here, especially those who implement these solutions, deal with. And if you had come to me, or probably a lot of people in this room 5 years ago, or even today, we would have come up with something like this for you. This is a pipeline. We would have suggested that you ingest all the data that you need, take as much time as it takes, then do the further pre-processing on it. If it's Sentinel, for example, run Centicore on it, so you have level 2, you would go on and create the cloud mask for them, whether you have your own algorithm or like maybe the data you're using actually has a cloud mask, and use that. And then go on and create the other products that you need from it. Here, there are many different approaches, but 5 years ago, I would have gone and for every field that I had, I would have generated all of those maps. This is a very common trend. Actually, the previous talk also showed another kind of diagram of how this could be done. I'm pretty sure almost everyone here has done this. But this doesn't work quite well for us. First of all, it's super expensive. Like doing all of these things, regardless of who is actually using it or how much is being used, it is expensive. It is sluggish, especially if you don't want to throw all the money at it. Obviously, you can, I guess, with today's computation powers, you can do everything fast if you want, but that's not the reality. You always have limited resources. This whole process takes a lot of time, actually. It's also not easily extendable. Like, it is a pipeline of connected things, and you can't just, change it the way you want. There is a lot of pre-processing. The previous talk had a very good example. Maybe someone changes something in the middle of it or wants another variation of your ARD or cloud mask or so on. Everything has to change for that. So what everyone has been trying over the last few years is this, where because of the improvements that has been happening on the cloud side, the storage side, and so on, it is actually possible, and there are many examples of it in the open source community, where you can actually have an on-demand service, where if you know what your image is, you know which area of it you want, you can actually, using that service, generate that image instantaneously. Obviously, there are some requirements. So, for example, the image has to be cloud optimized, meaning that you need to be able to read it partially, so that you would not be required to download the whole image, but just the portion of it that you need. There are a couple of formats, like GeoTIFFs, JPEG 2000. The SG presentation yesterday had very good overview of those. But again, this is not how it works, especially in our case, because whoever who is requesting that image actually doesn't know what images are out there that could give that map. You actually have to go and select the proper image for it. You have a cloud of all images, you have to search in it and find the image that can give you the right map at the end. It's on demand, so it has to be a really, really fast search service. Otherwise, the response time is not short enough, and the user experience is going to be really bad. just because I really like a STAC, let's imagine that really, really fast search service up there is a STAC. But I wish it was as simple as this. It's actually not. When you search, you get lots of images back. And one of them is the right one in our case that will give us that map. How would you actually go and choose which one is the right one? You no longer can search here for the right image because our metadata only tells us the average cloud coverage on an image. It doesn't tell us which pixel has cloud or not. So we basically have to kind of figure out how we can, on an on-demand basis, in less than a second, select the right image and give you the one that we want back there. So we actually ran a bunch of experiments on this. What was really interesting, and I guess, again, anyone who has done the software is pretty familiar with this, our bottleneck was the I/O part. Our bottleneck, whether the image is on the disk or you're getting it from the network, the bottleneck is the I/O. The actual processing part of applying the model or doing other things on it is the part that, in our use cases, doesn't take a lot of time. And obviously, there's a very good reason for it. Farms are really small relative to satellite imagery. And that really applies to all of our use cases. This might not be true if you are processing whole images or like, I don't know, the whole United States, but in our cases, this is the case. The majority of our time is on the networking, the latency on the network side. Even if it's on disk, it's still the first part of what you're seeing here is the bigger portion. Also, just to give you some context, like getting a raw image in that field size or getting like a model on top of it, this takes, in our experiments, with like data on an S3 bucket, less than half a second. So it's pretty fast, but it's still 87%, 70% of it is just getting the image. And so, just going back here for a second, we want to be able to select our images and then narrow them down in order to be able to give that map. And so what we're experimenting with and have actually shown that it works is parallelization. And this is really the key to our architecture. The bottleneck of I/O can really be sort of solved or actually taken to the next level when you read all of these things at the same time. And then the processing part is the smaller piece, and we have been able to, in a very, very short amount of time, reduce this stack of images into the single one that we need. And then we can expand it further and further. One key point here, which I'm going to actually go back to in a little bit in my slides ahead, is that a lot of the implementations of these on-demand services are either in Node or Python. I think the majority of them are in Python because the image processing part of it happens in Python. This is not what we are using here. Our stack is a Scala, combination of Java and a Scala. And the advantage that we have gained here is that the way that Java can handle threading is essentially like JavaScript on a steroid, because it has the full support for non-blocking asynchronous way of handling the I/O and network, but it also can distribute it across multiple threads. And there's very little cost of creating those threads. And when they are created, you can just keep reusing them. Something that I think is possible in Python, but it's not as straightforward. And we did get a lot of advantage out of that. In JavaScript, it comes out of the box, but you're dealing with a single thread, which could have some performance differences. And so this sort of on-demand approach will essentially enable us to kind of replace the sort of pipeline that I showed you earlier for us to go from the image that we have in the beginning to the final product that we want. But it also enables us to do other things. This is the kind of a future we're going towards, where because there is like this federation of sources, because hopefully there are a lot of providers that have the same catalogs, that you can search them, that point to public data sets, or maybe there are private providers who have private data sets, but if you have a contract with them or something, they enable you to access the data. Your on-demand service can use the same sort of like API interface to expand its reach beyond what Climate already has. That could really take out the ingest part for us, or at least partially take it out, which is super important. And then because we assume that all of that data is also going to be in cloud optimized formats and on places that are very quickly accessible, again, we can take care of the ingest part altogether. For the rest of it, as long as we have access to the raw data, we have experimented it and we have really shown internally that a lot of the processing that we are thinking about can be done in synchronous or near synchronous fashion. What I have at the bottom as a synchronous, I don't mean a pipeline. I mean something that instead of half a second might take 1.5 seconds or 2 seconds or 3 seconds, which is still a pretty short time. And if you have like specific SLAs that prevents from like having the client wait for a few seconds, then we can actually handle that with a kind of an asynchronous fashion, which is not a pipeline again, it's just near synchronous sort of approach. And this is important because in our use cases where our fields are small, everything is pretty much localized. Like in a lot of use cases that we have, everything are close to each other. We can employ a lot of caching. We can know access patterns. We can like make decisions about how we are building an architecture in the system based on those parameters, something which is really useful for us. And essentially, instead of having a pipeline that would give us the cloud mask, that would give us the ARD, that would give us the other things that we want, we actually allow the users, which could be our scientists, which could be other services within Climate, or which could be the actual farmers with their apps, to kind of decide what they get, and they only get it as they need it. And this also has a bunch of implications. It will definitely improve the experience of people who are using these services. If it's the scientists, they don't have to wait for a long time to kind of get to what they need, or they're not just blocked by the fact that we don't have a coverage for an area. If it's the user of the app, they can interact with the app and get results back almost instantaneously, instead of making a request and waiting for it to become available. It also, other than the experience, it also has a lot of like cost implications for us. In fact, when we do the pre-processing, there is just so much data that we pre-process that we probably never use or anyone ever touches. In this manner, we only produce what is needed. We cache it, we can make it available in a faster manner by caching it, and we know the access patterns, we know which users might be using it more, or if a scientist is doing a specific research at a specific area, and if they want to repeat it, because it's going to be cached the next time, the second time, the third time, they might even have a better experience working with this. And also the cost saving is really in the order of magnitudes, like really, really considerable cost savings. Some observations that I essentially mentioned, a lot of them. In our processing, the bottleneck is typically the I/O, but we think we can kind of tackle that bottleneck by doing non-threaded parallel image processing. I mean, accessing to the data and then processing it. And we have experimented, shown that it works internally. Our choice of Java, Scala in this case, and then the synchronous nature of it that is provided in Java 8 and forward has really been an important component of this whole effort. And we think you might actually get a better performance if you do it in Java, Scala versus like Python, for example. We care about the access patterns. That is going to be key on how we implement this. And fast search and discovery is super important. Like this whole thing collapse if you cannot find the images in the shortest amount of time. And obviously all the files that we have must be cloud optimized because we need to be able to read them partially. The future that we are going towards is really a future where we try to avoid ingesting everything. We only ingest the critical data. For example, if our production systems are going to be reliant on something that if it becomes unavailable, our business model collapse. So we might ingest those things just for production reasons. And also probably the stuff that we have to purchase and are not publicly available. We would only pre-process when there is a really clear advantage based on access patterns again. We might have those cases in the future. I'm not saying pre-processing should completely be put aside in our in climates, but it's something that is determined by how the data is accessed. The third point is, which was also brought up by the previous speaker, and I guess everyone's talking about it, we want to look at ARD as more of an API functionality than like some formula that you come up with and then you just go and generate ARD data. This is more likely going to work for our scientists, for our internal use cases, because context change, because requirements change, because the science around it change all the time, and also it's not clear what ARD is. And then one last thing that we are experimenting with, and it might happen actually very soon, is that we can actually move some of our image rendering and processing and even like some of the computational operations to the client side, especially on mobile devices. So that's our server side would essentially just provide the ingredients that are needed, and then within the client, in the iOS device or on the iPad, the actual maps are generated and so on. That would even increase the experience of our users further. It would probably bring down the cost further. It can allow us to take advantage of the fact that, you know, our use cases are localized, farms are near each other, so the caching within the devices can work in a better way. That's it. Thank you.
Questions for Alireza?
Two questions.
Not from climate. Oh, you can hear? I do have a
Yeah.
question.
Cool.
Oh, okay, take the mic.
Alireza, how are you? So this is very interesting to me. Can you tell me, when you're moving process into runtime and our clients are scientists, like you said, have you thought, or can you give an explanation or maybe your thoughts on how we're going to ensure that the rules are correct for their use case and how we can ensure quality to them? And how can we stop or maybe deal with their first inclination to say, just give me everything you can produce and let me pick?
Yeah, that's, so I think I can answer the last part of your question because that's the easiest. So there is definitely, I mean, this sort of model probably could work at kind of larger scale, especially if you're not interested in at the full resolution. If you're interested at the full resolution, then it would require a lot of extra resources. I think the way we should approach it internally is really to kind of put some sort of limits on the kind of things that you do, or also manage SLAs and expectations in terms of response time. Also, the asynchronous part of this whole thing could work for cases where you need something that would take longer than your typical response time. Having said that, I don't think we have gotten to a point to kind of also differentiate between the traffic that comes internally from the scientists for different use cases that they have versus the kind of a continuous production request that comes from our users and our apps. Yeah, and I think we should kind of find a balance there. But I think at the end of the day, the experience that everyone will have with this sort of on-demand approach is definitely better than what they get today because of just the limited nature of what we can offer, which is we can cover the whole world, we can cover all the data sets, we can cover everything that is out there because we are limited to what we are pre-processing. Whereas in this approach, you can really expand it as rapidly as the metadata is available or as the data are offered on different buckets.
It's green. Hello?
Hey.
So a little while ago, I was looking into, so reading these small AOIs from cloud optimized formats has some overhead to it. So a little while ago, I was looking at trying to come up with some rules of thumb of like, how big does that AOI need to get before you're actually better off downloading the file? Or if, how many times do you have to access the image before you should really download the file? So, but, I didn't do like anything like you're doing. I didn't look at a whole bunch of images. So do you have, you sort of hinted at this with the access patterns, talking about access patterns, but at what point is it really better off? Like these fields are going to be close to each other. You're going to have a bunch of fields. If you have fields that cover half of the tile, like at what point do you have a sense where it's better to just fetch the image and pre-process it and store that?
Yeah. I would say the only time you would need to get the whole image is if the field is the size of the image. I think anything below that, you really don't need to get the whole image. The reality is that especially if you use like Sentinel for the kind of use cases that we have, you never get even like slightly close to covering any considerable area of the map because of the parallelism that I described. Even if you're dealing with 20 fields next to each other, you might still want to make 20 separate calls and parallelize it instead of getting the whole thing. And the reason is that you're better off with the smaller pieces for the whole process than like one larger piece and doing image processing on top of that. And at the end of the day, the cost is still considerably lower than the pre-processing pipeline that we have. What we don't know, and I think that has not happened, and I don't think it will ever happen, is that the only time that pre-processing for us would make sense is that basically all of our users on a daily basis decide to look at all the imagery that we produce for them. And that is very unlikely. In that case, you could argue that maybe some sort of pre-processing might be cheaper, but it's still, even caching might work better there than trying to pre-process a lot of these things. That especially applies to like larger images because for a field to do some of our research on it or even generate the final map, we need the ARD for that field. We need the cloud mask for that field. We need those extra information just for that field, not for the whole tile. In a pre-processing approach, you usually just do all the things that needs to be done on the big tile first, and then you try to derive products out of it. And because of that, I think this sort of on-demand approach is probably always more cost-saving and faster. Any other questions? Cool. Thank you.
So next we have Youngryel from Seoul National University. And we'll hear more about crops, right?
Okay, good morning, everyone. I'm Youngryel Yu from Seoul National University in South Korea. So I'm scientist, I'm not engineer, so probably I'm going to talk too much about science, but I think it'll be very useful for your applications. So to my presentation today, I will show the potential way to monitor photosynthesis using CubeSats. So first, I want to thank the Rasmus Huborg. I think he's here. Oh yeah. So he supported a lot on this work, and also my group members, and Dennis Baldock at UC Berkeley, and big brains at Carnegie, Joe Barry, Grayson Batchelor, and Yalu Zhang. So just for your general background, what is photosynthesis? So let me start with the global scale, it is around, at the global land, it is annually around 120 petaton carbon per year. That is roughly global estimate of global photosynthesis. But to compare with that, so annual anthropogenic CO2 emission is around 10 petaton carbon. So photosynthesis is a lot. It is around 12 times of human release of CO2. But there is, of course, uncertainty. Yep. So if you look at the range of that, it ranges around 50, to 100 through 150. So the range of global photosynthesis estimate is around 50 petaton carbon. That is 5 times of anthropogenic CO2 release. So still there is a lot of uncertainty. And so photosynthesis is very important in terms of the climate system to understand the climate system better. But for your applications, it has direct relevance to food production and plant stress and also wood production. So it is all related with actual applications of remote sensing. And why that happens? So photosynthesis maps are typically, it is around 1 kilometer because the resolution. So GPP is photosynthesis. That the most widely used approach is light use efficiency. So that is the modeling framework. The photosynthesis is the multiplication of incoming light and fraction of the light that is absorbed by the canopy, and then light use efficiency. That is the fraction of absorbed light that is used by photosynthesis. If you look at each variable, the per incoming light is at most 1 to around 100 kilometers. That is available data set at the global scale or in regional scales. And F part, that is, we have fine resolution like from Sentinel or Landsat through the MODIS. So we have fine resolution. But in terms of light use efficiency, that is, I think I would say more than 1 kilometer because that is the function of air temperature, vapor pressure deficit, and soil moisture. So we don't have very fine resolution of those variables. So the intersection of all those 4 things gives around 1 kilometer, or if we don't have very specific local forcing data sets. But what we can do with 1 kilometer resolution for real-world applications in terms of photosynthesis. That is my country. There is my flux tower site in the rice paddy landscape in South Korea. So that is a CubeSat 3 meter, and Landsat and MODIS. I think even Landsat might be some limitations for actual applications in the in crop monitoring in this landscape. And if you think about 1 kilometer, that is 2/4 of that, MODIS 500 meters, then almost nothing that we can do in real-world applications. And then during my sabbatical leave at the Carnegie, I learned that there is quite new, actually old approach that is near-infrared reflectance of vegetation. And that concept was actually proposed by Pierre Sellers. That is, he passed away several years ago, but he was a very famous guy in the first biometeorology guy who went to the universe. He went to the International Space Station. But anyway, in his seminal paper in 1987, he argued that, let me briefly read here. If an experimenter were somehow to launch an equal number of visible and infrared photons at a vegetated surface, he could estimate the number of visible photons absorbed by the vegetation by counting the refracted near-infrared photons. So if we can quantify the near-infrared photons from vegetation only without any contamination of the soil or background, then we can estimate how much photon is absorbed by the canopy that is used for photosynthesis. That is quite old. It is 1987. That is quite old, but just let me briefly explain one more term. That is SIF. That is very fancy variable. That is very, I think the Hamed has very nice paper as well. So SIF is ultra-fine spectral system is required less than 0.2 nanometer. It is adopted in OCO2, OCO3, and ISA flex mission. They are all going to use this sun-induced chlorophyll fluorescence to monitor photosynthesis. That is very expensive, very narrow band. But what we learned that, so NIRV, that is the index that was proposed by the Grayson Bachelet, Joe Barry, and Chris Field at Carnegie. And that is based on broadband, very cheap, very inexpensive. NIRV is simply the multiplication of NDVI and infrared reflectance. Just broadband, 20, 30 nanometer. And then it is a sort of spectral of mixing method. So to account only for the infrared from vegetation only, that NDVI is a sort of scaling factor. So 0 means no vegetation, 1 is 100% vegetation. Of course, it is not correct, but it is good first order approximation. And then they compare the NIRV with that is very expensive variable. Then they found that this broadband can explain most of the variations of SIF. And then when they compare with photosynthesis, then this NIRV can perform better than SIF in predicting photosynthesis. And so there is something is there. So this broadband, that if you have very well calibrated red and infrared, then you can predict photosynthesis. And now my group is working on that, so we tested based on the field observations. Oh, hello? Okay. Okay. Yeah, so we are testing 3 major crops, rice, wheat, and corn. And we found that here y-axis is photosynthesis, field observed photosynthesis, and x-axis is several variables that are related with SIF. But the key message here is that if you compare the R-square, the highest case appears at the last case. Here from 0.43 up to 0.75. 0.45 through 0.55, 0.51 through 0.82. And that is exactly the case of NIRV multiplied by par. So that means once we have just 2 broadband, red and infrared, and the incoming light information, then that can predict photosynthesis best compared to even perform better than very expensive SIF variable. And that includes from half-hourly through seasonally, so it can track the photosynthesis across the time scales. And then 2 months ago, I invited my PhD advisor to my university. And at the time, he has multiple flux towers in the California, and one of his flux towers is located in the Tule, in the wetland. He has the photosynthesis data set. He measured from the flux tower, but when he tried to model, he could not because the ecosystem is too complex. There is green, also yellow, different colors of the vegetation, and some vegetation are collapsed, and there is also water. It is a disaster to model. So he could not model, but we discussed and he just plot NIRV. Here, x-axis is NIR outgoing radiation and multiplied by NDVI, and y-axis is photosynthesis, and it just linear. We were shocked. This simplification worked very, very well. And then he expanded that analysis up to wetland, and alfalfa, and corn, and we found all very strong linear relationships from half-hourly through seasons. It worked very, very well. Just simple index. Okay, so then wait. So this NIRV that only requires just two broadband, red and infrared. And of course, the best case is the red and infrared radiance at the surface. That will be the best case. Of course, then we need to atmospheric corrections. And actually, that's what CubeSats, like Planet scopes, can provide at 3 meter daily globally. Then why not using CubeSats to monitor photosynthesis at very fine scales? And that is, there is a flux tower in the rice paddy landscape in South Korea and that is a Landsat, and there's CubeSat. You can see the clear advantage of the CubeSat. And we know that CubeSat has, the spectral quality is not great, but thankfully owing to the Rasmus this work system, then last year I read his paper and I was just excited, and I contact Rasmus and hey, that is great. And yeah, because then we can use the CubeSat to, we can get very fine resolution and also high quality surface reflectance information from the system. Then why not using NIRV to monitor photosynthesis using system? Okay, so I'm a scientist, so always my advisor stress that don't believe anything without calibration. So calibration. So I think the satellite data too. So it seems you are all based on the end users, but I want to test. So that is the flux tower site in my country in South Korea. So here there is a flux tower and the eddy flux system here that measures photosynthesis at the ecosystem scale. And we have a bunch of the hyperspectral system, QPro that is for sun-induced chlorophyll fluorescence. And we have that is ocean optics, just for visible to infrared hyperspectral sensor. And we have multiple broadband spectral system here. So there are many spectral sensors. And so we tested the system. First, we tested the surface reflectance across the seasons. So that is blue channel, and blue band, green band, and red band, and infrared. And the blue color is the system, and red is in situ spectral data set. So overall, the system surface reflectance will capture the seasonal variations of surface reflectance. Although there are some bias during the ripening stage of the rice, here the system tends to be lower than in-situ observations. And then we tested the NIRV using the based on system and also based on field observations. They are very tight, show very linear relationship, although there is some bias. That is because of that during the ripening stage, we found that the system was higher than in-situ observations because of the bias in the surface reflectance, particularly for the near-infrared. But overall, it looks pretty good. And then we also tested the system across the landscape scale. That is, blue is the modest pixel, 250 meter modest pixel, and my student collected the hyperspectral reflectance data set at the surface across the whole seasons. And then we compare with different image fusion products. I just screened out the name of the products, but I just showed the system here. And here x-axis is in-situ NDVI, and y-axis is the system and the image fusion product. And we found that the system NDVI performed very well. It captures spatial variations as well, spatial variation also, and also temporal variations. So it looks quite promising. So that is the rice landscape in South Korea. That is where my flux tower is located in Cheolwon. And so that is the NIRV map. And I was very happy with that. So even in South Korea, the landscape is highly fragmented. So plot is very small. So one plot is less than around 30 by 90 meters. So just 3 landscape pixels. But by having CubeSat-based NIRV map, then we can see all detailed spatial variations within the plot and also across the plots. So I think it has great potential to monitor photosynthesis at very high resolutions. And also flux tower is based on micrometeorological theory. So the photosynthesis estimate is dependent on the wind speed and also wind direction. So there is certain footprint of the flux tower observations. Here is 70% of contributions comes from around this area. It is around 300 meters. And so if I use MODIS, the MODIS single pixel is greater than that footprint. But by having CubeSat, then we can look deeper into the distributions of photosynthesis within the footprint as well. So it has great promise. Then the next topic is still we have to test and calibrate, evaluate. So during my PhD, my advisor developed such small LED-based spectral sensors. So after I returned to Korea, I replicate the sensors with my student, and we spread across diverse ecosystems in the world. And it's just one sensor is around $100, so it's quite cheap. But it worked pretty well. That is in-situ NDVI time series. And because NDVI is red and infrared, so of course we can compute NIRV as well. So across diverse ecosystems, all the sensors show that continuous whenever rain, windy, whatever happens, and always it can measure because it is near the surface, around several meters above the vegetation. So we can see very high precision that can be used as a reference to calibrate and evaluate satellite sensing data set. So that is my final slide. So that is one image of the low Earth orbit satellite. I see there are the CubeSat, the Planet scope is one of them, and there are many, many opportunities. But they must be tested and calibrated. So I think now we are commercializing our sensors, and then those sensors include now 4 to 5 channels, similar with Landsat or Sentinel, from visible to infrared. And we are trying to replicate and install those sensors across diverse ecosystems to then those information will be useful for calibrations of those CubeSat images. And then I think we have even better opportunity to monitor photosynthesis at very high spatial and temporal resolutions. Okay, so that's the take-home message. And I think once we can monitor photosynthesis at very high resolution, then it will have many applications in crop monitoring, forest, and plant stress detections like that. So, yeah, thank you very much.
I really enjoyed your presentation. Couple questions. For the purposes of your discussion, what is one photosynthesis unit?
Photosynthesis unit is, of course, first is micromole per kilometer per second of CO2. That is a snapshot. Whenever satellite overpass, that is a snapshot of photosynthesis. And there are several methods to scale up this snapshot information into daily sum. And then, of course, then we can add up into weekly, monthly. Yeah, it is all.
So if you have one snapshot at one time per day,
yes,
we can reliably extrapolate over the distribution of the rate of photosynthesis for the entire day, like what that might have been, because I assume it changes throughout the day, right?
Yeah, there are several papers on that. So because now there is global network of photosynthesis observations from the Flux Tower, and when we tested whether single observation could represent whole day, as long as we have the potential solar radiation information at the top of the atmosphere, it can be done reasonably well. And also we have multiple choice as well. In case of MODIS, we have Terra and Aqua, so 2 times per day. And so, of course, we have more and more information within the day, then, of course, the accuracy will be better. And if you think about geostationary satellites like GOES or Himawari, then it is every 10 minutes. So, and just one snapshot per day is still can predict daily estimates pretty well.
Okay. So my only other question is, I guess it's kind of 2, and I'll let you answer whichever one you want. But are you aware? I think you showed some great examples of where your approach works really well. Are you aware of any areas where this approach doesn't work very well?
And it seems to work very well when we test it. The site where we tested, but we didn't test for example, in the Amazon, we didn't test.
Okay.
And so we are trying to expand the analysis, but at least based on very coarse resolution, like 0.5 degree, 50 kilometer resolution. In the case, it seems it worked well across the whole globe.
Do you think this could work with phytoplankton as well?
Sorry?
Do you think you could measure photosynthesis of phytoplankton with this approach?
Which planting?
Oh, like different types of algae in the ocean, like phytoplankton.
Oh, ocean. Oh, ocean. We are only focused on the land.
Okay. Thank you.
Okay.
Your advisor is a very wise man with his emphasis on Calibration. But it's not this is it. I could just talk about it. Yeah, because we are recording, so it will help. Anyway, your advisor was a very wise man with his stressing Cal and Val. How, with your emphasis on the CubeSats, how does the calibration of the CubeSats affect your results, and what would you like to see different in what would help you in the future?
So your question is how calibration of CubeSat data could help to predicting GPP photosynthesis?
Yes.
Yeah, of course. First step is we have to get the right surface reflectance or surface radiance of red and infrared. So if that is biased, then of course photosynthesis estimate will be biased. So I think the first step is to make sure that the surface level, surface reflectance or surface radiance must be good enough. And if it is biased, then yeah, photosynthesis estimate will be biased. So yeah, I think still we need ground-based data set.
I have just a minor question. If I remember correctly, the solar-induced fluorescence has a unit of radiant power per square meter per steradian per nanometer. So it's a radiance. Then how do you control the varying solar conditions, solar zenith angle, and varying atmospheric conditions?
Okay, yes, that is very technical, also very good question. So in case of solar-induced chlorophyll fluorescence, there are two approaches. One is based on Fraunhofer lines. In case of the Fraunhofer lines, that's, for example, OCO2 or OCO3, because they only look at the Fraunhofer line, that is, atmosphere is transparent. So it is free from any atmospheric interference. But in case of the flex emission in the ESA, that they rely on the O2A band, that is highly sensitive to oxygen level in the atmosphere. So correcting all these atmospheric processes is very complex, and it seems quite challenging. So these two groups between Fraunhofer line group versus O2A group line group, they are all debating together what is better. But it seems Fraunhofer line seems better, but they have to rely on extremely narrow band, like 0.1 nanometer. So then signal to noise ratio is very, very important. Okay, thank you.
So our next presentation is Bruno from King Abdullah University of Science and Technology.
Hi, good morning.
It's not there, sorry.
No. Okay. Hi, good morning. My name is Bruno. I'm going to base this presentation on data fusion and a little bit of the journey that you have to travel to compute crop water use. And in this case, using Planet CubeSats and a model that's called the Priestley-Taylor Jet Propulsion Laboratory Model. So a little bit of background on why we want to maximize water use in agriculture. I really like to look at this image a little bit frequently to remind myself of how much water is available in our system. If you see that big bubble over the US, that's all the water that we have on the planet. That's basically distributed in underground, ice caps, lakes, rivers, oceans, everywhere. The smaller one is the liquid fresh water. So that's not including the water that's in the ice caps. And that other smaller, I can point, okay. And this smaller bubble over here, that's the water that we can actually see on rivers and lakes, which is a very small quantity. Why is this important? Because as I think everyone knows, one of the primary inputs to agriculture is water. And the food demand is increasing everywhere. This is important because our current systems are already starting to be stressed and reaching physical scarcity in some areas of the world. Where I come from, which is Saudi Arabia, I think it's not surprising to anyone that is very water stressed, as it's basically a desert country. And in spite of this, agriculture in certain parts of the kingdom has boomed over the last 2 decades or so. If you see in these images, it's a Landsat time series of agricultural development over the kingdom in a region that's called Al Juf. Every little speck of green that you see here is a field of 54 hectares approximately. And if you want a rough estimate of how many fields there are in there in this image, it's around 3,000 of them. And how much water do they consume? Well, it's a desert, it's very hot, it's dry, so the answer is a lot. And the only way to irrigate all of these fields, since Saudi Arabia has little to no precipitation, almost has well, I would say no significant water bodies to provide the water. All of this comes from underground. And since there is no precipitation, these are fossil aquifers, which are depleting at a very high rate. Here, a colleague of mine did a little study that used grays to estimate how much this aquifer was depleting every year. And it was not a surprise that the answer is a lot, and it has been decreasing quite rapidly. Recently, the government of Saudi Arabia started to take interest into this. So a lot of money is being poured into how much water is currently used, because paradoxically, water for agriculture is free in Saudi Arabia. So the kind of good practices that there are here in the US are almost non-existent there. And how can we solve this problem? Well, we need to maximize the amount of crop that we get per drop. And how do we do this? As we have heard from several speakers here, the only option to do this is by fusing multiple data sources into one and to inform the farmer at a proper time step. To iterate a little bit on the importance of spatial and temporal resolution, underneath this image, you have four views of the same area. First, of course, this is Saudi. First, you have the MODIS pixel, which completely misses what's underneath. Then you have Landsat, which is quite good, if I may say, for these fields. But going over to Sentinel, you can see that some of the field heterogeneity that was not visible in Landsat starts to be visible. Then you have Planet CubeSats, which brings us a step further into this. Over here is a sample field. As you can see here, there is a lot of heterogeneity in the field that sadly is not visible from the ground. So usually the farmers, which are very traditional over there, don't have a clear way to visualize this. And in here is a little footprint of what represents a CubeSat pixel and other finer scales. But it's not only important to look at the spatial resolution. We also have a problem on the temporality of the images. Here is a simulated measured LE flux over agricultural site in a given season. And as you can see, Landsat time series could miss the high peaks or giving erroneous results under periods of inactivity in the fields, which is fairly common if we have interference by clouds or, in our cases, dust storms. So we may end up with a couple of Landsat images across the growing season and not be able to properly resolve how much water is actually being consumed. Sentinel-2 brings us a little bit closer to replicating the actual evaporative flux that is present in there. But what if we can take it a little bit a step further? For instance, CubeSats from Planet gives us this opportunity. As you can see here, missing a couple of images is suddenly not as critical if we want to track daily water consumption. So why don't we readily use the CubeSats for agricultural purposes or precision agriculture? Turns out that, as was explained already several times, there are several challenges if we want to use the raw data provided by Planet, such as different qualities in the spectra of the images compared to a commercial sensor, government sensors such as Landsat or Sentinel. So we need first to do a harmonization process in our datasets and correct these CubeSat inconsistencies. As the previous speaker mentioned, one of the best approaches to do this is by using the system framework developed by Rasmus Huborg, in which he employs a machine learning approach to fuse MODIS, Landsat, and CubeSat images. That in the end result is that we have CubeSat images at 3-meter resolution with higher spectral qualities that we can then apply and derive vegetation indices such as NDVI, or also derive a leaf area index, which is arguably a better variable to track vegetation. So, digressing a little bit, how do we estimate water consumption with our images? We know that from the reflectance, we can infer plant and stress condition. That's, I think, a common topic in the presentations. And then we have another view of it. We can view the incoming radiation as energy that is being transformed at the plant level in either heat or evaporation. You can think that plants have, well, they do have pores called stomata that plants use to basically sweat, transpire for photosynthesis purposes. And the plants are very smart, and they can regulate how much water they evaporate by closing or opening these stomata. So we reach something that's called the energy budget. Incoming radiation must be equal to some energy fluxes. In this case, we have the sensible heat flux, ground heat flux, and the latent heat fluxes, which are evaporative fluxes to the environment. This evaporative flux can be combined into something that we call evapotranspiration, which is measured in water depth, and is closely related to the water budget. In our case in Saudi Arabia, ET is basically equal to the amount of precipitation or irrigation that we have in the fields. So our system is quite simple in a way of the water budget. We don't have surface runoff, and ideally we don't have subsurface runoff because we want to be irrigating at just the necessary amount. So just to reiterate, this is the complete picture, and why ET or evapotranspiration is a key variable that links energy to water. And it also links to food production, because this is one of the main variables that we want to optimize to get better yields in our fields. A typical overview of this water retrievals framework is something like this. We do need to have some field data, ideally, because our models to compute it, or most of them, rely on in situ data. It can also come from reanalysis, but at very large scale, which may not be representative of what's underneath. Also, as was mentioned before, we really want to have an idea of how accurate our predictions are. Sometimes if we give farmers an indication that they should irrigate or that they shouldn't irrigate, that has a very serious implication on how the field will react. It can mean that either they will lose half of their harvest or they will actually produce more. On the other side, we have the remote sensing approach, which is a combination of several sources. It can be from the optical, and we need to do an atmospheric correction if we want to use these data sets. In the terms of LST or land surface temperature, we need to have some physical simulation that's called a MOTRAN to atmospherically correct, but I digress a little bit. Then all of this data is fed into our models, which compute an ET product that we validate with field estimations. The two models that I've been using mostly are called TSEP, the two-source energy balance approach, and the Priestley-Taylor jet propulsion laboratory model. These models are a little bit different between each other. TSEP actually computes aerodynamic resistances to compute these evaporative fluxes. And Priestley-Taylor uses a scale version of the Priestley-Taylor equation to get a partition of actual fluxes of evaporation into the environment from canopy, soil, and interception. So now that we have all of this, how do we validate these fluxes? Well, we rely on an instrument that's called an eddy covariance tower, which relates the variations in wind in the eddies to a variation in mass, such as H2O or CO2. And this measurement is not a point measurement or not even a fixed measurement as we would like. It has something like this, which is an envelope that doesn't have the same weight. It's a weighted function. So before even validating at the scales that the CubeSat enable us to do these simulations, we really need to have a footprint integration process being done there. And I don't know why my reference doesn't come here, but the one that I use is also the Natasha Klugen's approach. And before showing you the results, this is an image of the experimental farm that I've been studying. It's located in the middle of nowhere, literally. There is not much going on there. It's just desert with specks of green. We have installed some weather stations, and most importantly, the eddy covariance tower. And here it's being cleaned together with the satellite that we have there. It's a little joke, it's the moon. And yeah, so using Planet CubeSat imagery, we managed to obtain the highest ET retrievals from space that really reflect a clear picture of how heterogeneous these fields are. For instance, if we see here, we can see that this part of the field is not performing as it should be. And that's something that the farmer should really take into account. Either in the case of Saudi, it's mostly related to the soil quality rather than the irrigation, because the irrigation arm just constantly irrigates at the same rate. But the crop is actually under some stress that we can detect from space using weather and optical imagery. So how are we validating this model? We use the eddy covariance measurements and our modified Priestley-Taylor model, which is quite encouraging given the location of our forcing data, which is at the edge of the field. This also has some practical implications. You cannot readily rely on weather data. You have to have a little bit of context of where it's being collected. As was previously mentioned, field experience and hands-on approaches are a must. It's very easy to just be back in front of the computer and click run and give a number. But if that number doesn't have the appropriate context, it could be fairly off. Even for validation, you need this kind of context. And again, why do we need high spatial resolution? Because our fields could be highly heterogeneous. The scale of our fields may be very, very small. And what are the impacts of these scaling issues into our crop water use estimations? Here I kind of simulated a bit with the different footprint sizes over the field that had the eddy covariance tower. And again, just I did an aggregation at field level, which is what's typically been done at large scales, and found that between Sentinel and Landsat and CubeSat, there is not much difference if we look at a very large area or at a large field level, as I must say. But once you start to reduce these field sizes, you can start to see the impact of having large pixels, which cannot resolve the field heterogeneities or have severe edge effects. In here, you can see the image, the histogram from Landsat 8, and most importantly, the difference compared to the value that we retrieve from CubeSats, which are around 30%. That's quite significant. The difference with Sentinel is not that much, but the signal is already starting to degrade in the histogram sense. And as this becomes smaller and smaller, we will clearly see the advantage of having finer pixel resolution. And I want to close a little bit of my presentation just to mention that is visual and near infrared enough to actually track water use? And the answer is a little bit complex. It depends. It depends on the crop. It depends on the stage of the crop as well. For instance, this is maize on early stages with a very quick run with uncalibrated models. I use TCEP, the classical PT-JPL, and a PT-JPL version that uses thermal imagery with Landsat. PT-JPL, the one in the center, is only an optical-based approach. And as we can see, it's remarkably different from the other ones. Why is this? If we look at the partition fluxes, which is the flux in the canopy, we can see that the three models have a very similar spatial distributions. The thing is, once we go to the soil component of these things, in the early stages, the canopy is not fully developed, but still the field is being actively irrigated. And we lose this signal, this information, if we don't have a thermal input in there, or at least a very good proxy that informs us of the real soil moisture status. As quick conclusions, I want to highlight that we really do need a high frequency overpass, high spatial resolution, which Planet plays a vital role in this. We need sadly, we need frequent LST more than what is currently available. There are some missions such as the EcoStress one, which gives us LST at every 3 to 5 days, depending on luck at varying times of the day. 70 pixel resolution, which is better than the Landsat one, but arguably still not enough. And that we need to really be careful on ET estimations precisely because of this. If the major component is canopy transpiration, visual methods do really give us a clear indication and good benchmark to inform the farmer. But this could be a very big issue in the later stages or in the beginning stages, or also for crops that are quite short as well. With that, I'd like to thank you and receive any questions that you may have. Thank you.
Yeah, thank you very much. It's a very interesting talk. Did you try to evaluate albedo? Because the CubeSat does not have shortwave visible infrared region. So just, first question is did you evaluate albedo? And second question is, did you evaluate net radiation from the tower?
Yes, the PT-JPL normal approach uses net radiation as input from the tower, so we do lose that variability. For albedo, that's something that I started to look recently as part of an internship that I did. These models are highly sensitive to net radiation, so we do need to find an approach to estimate albedo with CubeSats. I still haven't zoomed in into how I'm going to do this, but yes, it's definitely important, because if not, albedo makes us think that we have a different net radiation variability than we actually have. And that is the difference between estimating a developed crop or a non-developed one, if we rely on Landsat imagery for albedo, which can get quite outdated. But sadly, albedo from Landsat is already ingested in some approaches, such as the EcoStress evaporation algorithm uses Landsat albedo instead of more frequently sources. You can see some of the artifacts in there in their datasets.
I'd like to make a really minor comment now. You compared to 30 meter only pixel and 10 meter and 3 meter the dynamic range of min-max value of pixels, right? So as if 3 meter planet is kind of superior. Yeah, but if you compare it to worldview 1 meter or half meter data set, you can have the exactly opposite situation. So I mean,
Yeah, definitely
right. Big
elaborating
pixel
a little
average
bit on your observation. Also in the modeling part, a lot of these models were derived with a mixed pixel representation of the surface. So yes, if we zoom in and start to look at to UAV approaches that we have decimeter pixel sizes, sometimes these models, especially the resistance part of the model, starts to break out into a very ugly result. Thank you.